Let's do the Lewis diagrams of CH2Br2. So first, we always calculate the valence electrons. And if you look at carbon, carbon would have 4 valence electrons. Hydrogen, each one of them would have 1, and I have 2 of them. So 1 times 2. And there's 2 bromine. And if you look at bromine on periodic table, it's on group 7. So each of these bromine would prefer to have 7 electrons, and there's 2 of them. So if we simply count the total number of electrons, we have 4 plus 2 plus 14, so we have 20 electrons in total. Okay. Now, let's look at the preferred number of electrons, and I'm going to use a different color in this case. Now, when we say an octet, that means the central atom, in this case, carbon, prefer to have 8 electrons. Okay. And the rest, how many electrons does hydrogen prefer to have? 2, and there's 2 of them. And how many electrons does bromine prefer to have? 8, and there's 2 of them. So as long as it's not the central atom, you can just assume that it prefers either 2 for hydrogen or 8 for anything else. There's a handout in the front, and there's also some activity that I want you guys to do in a bit. So we're just going to add it up together, and you'll find that this is 8 plus 16, so that's 24 plus 4. We have 28. And if we look at the difference between the two, we have the difference of 8, and we simply divide it by 2. We know that this molecule has 4 bonds. Okay. So if one were to draw the Lewis diagrams of CH2Br2, I'm going to draw carbon in the middle, and then I'm going to put hydrogen in the same corner. We'll get to Y later, and I'm going to put the bromine on the same corner too, in this case the top. I have 4 bonds to give, so I'm going to give 1, 2, 3, 4. Carbon prefer to have 8 electrons. So carbon prefer to have 8, so I'm going to count 1, 2, 3, 4, 5, 6, 7, 8. It has 4 bonds. So carbon is happy. Hydrogen prefer to have 2 electrons. It's also happy. But the bromine prefer to have 8. So far, it only has 2 electrons from the 1 bond that it has. So I'm going to give it 6 more electrons. Same with the bromine on the top. I'm going to give it 6 more electrons. And now we're complete with the Lewis diagrams of CH2Br2. And in this case, this is an octet because the central atom prefer 8 electrons. And that's why I'm highlighting the central atom with 8. So far, so good? Now, I want you to try on your own to draw the Lewis diagrams of BF3. I'm going to leave you in terms of calculating the valence electron on your own, and I'm going to give you a hint in terms of the preferred number of electrons of bromine. Boron in this particular molecule prefer to have 6 electrons. Whereas the fluorine, because it's not the central atom, it's still going to prefer 8. And there's 3. By the way, what's the valence electrons on boron? Where is boron in the periodic table? 3, thank you. And fluorine valence electron is 7, and I have 3 of them. All right, so on your note, as well as on the board, when you're ready, or you can play around with the board first, when you think you got the answer, flip it up to me, and I say A or nay, and then we'll finish it off as well. There's a handout in the front if you haven't gotten one. There's also a board if you want to play around with this thing as well. Yep, thank you. Yeah, I couldn't see the. Yep, that looks right. I couldn't see the dots there, so it's hard to see. Anybody else want to share their answer with me? So this is 24. 24 plus 6 is 30. So that's my hint for you, is that if you count everything, thank you. There's a lone pair in there, right? I can't see the dots. Yeah, thank you. It's tiny dots. Yep, thank you. That looks right. So we have 3 bonds to give, and essentially you just count from there. So I have boron in the middle, and I'm going to kind of spread out the fluorine into 3, and I give out 3 bonds, and I'm done. I don't have any more bonds to give, and boron, in this case, prefers 6 electron. So I'm just going to count around boron, and I have 1, 2, 3, 4, 5, 6. So boron is now happy. But the fluorine is not yet happy because it's only 2 electrons around each fluorine. So I need to give it 6 more to go. Okay, and I'll do the same with the rest of the fluorine. I'm going to give it 6 more electrons to go. And now this is the complete Lewis diagram for BF3. This is less than 8 in the central L. Now, any questions on the Lewis diagram for now? No? So let's do the harder one, because in this case, PCl5 will have greater than 8 electron. But I'm not going to tell you how big is big. So there's a quirky thing in terms of we're just going to limit ourselves with the central atom either having 6, which is the less than octet, or having 8, which is exactly octet, or we can also have 10 and 12. Right? So your expanded octet for our preliminary chemistry class is either going to be 10 or 12 electrons in the central. Okay. So the question is, which one is the correct one for PCl5? You can guess, but the best way to go is just try to calculate it. So I'm going to guess, and I'm going to guess incorrectly. Right? So this is going to be an incorrect guess. So let's just say I'm going to count my valence electron because that's always what I have to do. The valence electrons in phosphorus is 5, and each of the chlorine have 7 valence electron, and I have 5 of them, so I multiply by 5. So the sum of the valence electron in total is 40. All right. So what I don't know is what is the number of electron that phosphorus prefer to have. Okay. So I'm going to guess incorrectly that the phosphorus prefer 8 because I'm just starting out. So, and then I'm going to add each of the chlorine prefer 8, and I have 5 of them. So what happens is that if I do this calculations, I have, in the end, 48 electrons. If I were to try to calculate the number of bonds, the difference between the two is 8 divided by 2 equals to 4. So if I were to try to draw the diagrams, I have phosphorus, and then Cl, 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 I have 5 chlorine. But I only have 4 bonds to give. So 1, 2, 3, 4. I don't have any more bonds to give. So that means this is wrong. So this is wrong. Right? So in order to make it, I have 5 chlorine in here. So at least I need to have 5 bonds. So if you remember, each bond counts as 2 electrons. So I'm just going to move, I'm missing 1 bond. So I'm just going to move from 8 to 10. So that means my central atom in the correct diagram will prefer to have 10 electrons in total. So if you recalculate everything again, 10 plus 40 equals to 50. So the difference between the two is 10 divided by 2. So I have 5 bonds to give. So the proper Lewis diagram is now, I have 5 bonds to give. So the phosphorus is happy because it has 10 electrons. And I'm going to make the chlorine happy by giving it 8 more electrons in each one.
How can we change the number? How can we change the number for phosphorus to not 4?
The chlorine, only the central atom is going to have expanded octet. The chlorine in this case, or what they call the ligands, wouldn't share more than just want to have 8. It has a lot to do with the central atom is being tugged and pulled from a lot of different sides. That's why it has to share a bit more electrons. Otherwise, because it's just bonded to the ligands, in this case the chlorine, only bind once, so it doesn't have that force where it's being pulled apart. So it doesn't like to share any more than just 1 in this case. So this is the Lewis diagram for PCL5. Right? So essentially what I'm trying to tell you is that if you guess incorrectly and you thought it was an octet, and you calculate the number of bonds and you realize like, whoa, I don't have enough bond to give, then if you're missing 1 more bond, just keep 1. If you're missing 2 bonds, keep 2 sides, and that means your central atom has 12 electrons. Yeah. So even if you guess incorrectly, if you're missing a bond, just move 1 down. If you're missing 2, you move 2 way down. So any questions on this one so far? On the expanded octet, there is a bit of a guessing game, and sometimes you can make your guess a little bit better. For example, if I were to see that, oh, I have 5 chlorine attached to the center, so at least I need to have 10 electrons in the center. So you can make that kind of educated guess as well. Sometimes it's going to be correct, sometimes it's going to be wrong. So, but your guess is going to be fairly decent if you follow that rule. Sometimes, and the best way to go is that once you realize that your molecule look like an expanded octet, do the calculation. That way you're not going to make a mistake. Expanded octet are quite tricky. Sometimes what I see a lot is that people confuse which one have 10 electrons, which one have 12, because it's not particularly clear. So on your board, any questions about the expanded octet for now? Nope. So on your board, I want you to do, let's do, I think I have double, let's do XEF4. So it's the second to last on your list. So I want you to do on the board with your colleague, if you have a board with you, try to draw the proper Lewis diagram of XEF4. All the lists that I have on the bottom there are going to be expanded octet, but I'm just not telling you which one and how many electrons there are in the center. And again, the rule is try to count the number of bonds. Oh, you're doing SBS5. Sorry, my head is on XEF4. I don't remember either, so I have to calculate it too. That one is wrong though. No, the SPF5, I don't think it's the right one. Do I have a periodic table with me? Oh, you know what? SBS5 is correct. I was going to write SF5, but it's a different thing. So that one is correct. Yes, that's correct. So how many electrons in the center? All right, so that's supposed to be 12, right? Yeah. Anybody got an answer for me? I think this is one of the lists that you have. If you've already taken the Lewis diagram lab, this is one of your questions as well. So if you solve this one, then you have that one already solved for your lab. Not quite. Wait, let me just double check. Yes, that one's right. Let me just double check. Sorry, the dots are hard to see. No, that's not right. So it's not an octet. It's an expanded octet. So the central atom would have more than 8. Oh, you didn't get one of these? Oh.
But I don't have it with me right now.
Oh. Yeah, that looks right. That one looks right.
Set. One.
XE is right there. SB is right there.
That thing has about 5.
Yeah.
So let me get this straight. So normally in an octet, like for these guys here, these would be octets, I think.
Carbon is octet, so it's just essentially this row is usually octet.
Beryllium here is not an octet.
Sometimes.
So
Yeah.
but I remember from my chemistry lab, I saw something that beryllium is bonded to 2 fluorines, and all it was having was just 2.
Yeah. Beryllium in that case have 4, which is a bit odd, but yeah.
It's a strange thing.
Yeah. Yep, thank you. Oh, you're doing SBF 5? Yes, that's right. What's up?
Oh, we're supposed to do this?
Yeah.
Oh, okay. I did 12. It's 12, it's 12, right?
Yeah. Hold on. This is not quite right. How many electrons is in the central atom as you're drawing it now? So there's 1 bond, 2 bond, 3, 4, 4 bonds. Each bond counts as 2, so you're missing 4 more in the central. Yeah. Yep. Oh yeah. Can you put this on the side so it's easier to see? Yep. Thank you. Not quite. Almost. All right. So I think half of you guys are almost there, or getting pretty close to it. So here, the answer is that the central atom would prefer to have 12, right? And even if you guess incorrectly, you still be able to get to the right answer. So let me show you a way that, suppose that you do this incorrectly, and you suppose that it's preferred to have 8 electrons. So if you calculate this one, 8 times 4 is 32, plus 8 is 40, and you calculate the number of bonds, this is 4 divided by 2, so you only have 2 bonds, right? And you have 4 fluorine, so that's not right. So this is your first guess, and it's incorrect. You need to have at least 4 bonds, so I'm going to move 2 step over. So you need to have 12 electrons in the central atom. If you have 12 electrons in the central atom, this is going to be 44. The difference between 44 and 36 is 8 divided by 2 is equal to 4. So we're going to have 4 bonds on XeF4. And the way to draw this is that we're going to have xenon on one side. And I'm not going to explain why I'm drawing it this way first, but I'll do that later. So I have 4 fluorine. Oh, not iron. Fluorine, excuse me. One of them is pointing towards the board, and the other one's going back towards the board. And then I'm going to give each fluorine 8 electrons. So 8 electrons on each fluorine. So the fluorine is happy, but this is more or less where I see some of you guys stop. And don't forget, your central atom prefer to have 12. And so far, your xenon only have 1, 2, 3, 4, 5, 6, 7, 8 electrons. So we need to give it 4 more to go. So I'm going to give it 4 more electrons to make it a complete number of electrons that it prefers to have. So the Lewis diagram of xenon tetrafluoride would look something like this. Just don't forget, your central atom no longer have 8 electrons, so make sure that you count the number of electrons in the central, and it's exactly the number that you prefer to have. Again, if you guess incorrectly, just kind of move. If you need 1 more bond, just move downward to 10. If you need 2 extra bonds, move down to 12. Right? So if you do it that way, there's very less chance that you're going to make a mistake. Let's do BRF3. I think this is, yeah. So let's try to do BRF3. Please draw the Lewis diagram of BRF3. By the way, majority of these are going to be in your Lewis diagram lab. So anything that we don't finish today, you're going to see it again in the lab. And anything that you finish today is going to be useful to make your lab a little bit shorter as well. Yeah? Oh, this one? I'm easing into geometry. So geometrically, this is actually pointing out from the wall, and the other one goes into the wall. So I'm trying to show it that it looks like that. By the way, this is this geometry called a seesaw. And if you look at only the atom, you have fluorine in the middle, and you have you have fluorine on the two sides, and then you have two fluorines on the bottom like that. So it looks like a seesaw because yeah. Anyway, that's why it's called a seesaw, molecular geometry. But that's maybe on Friday. Thank you. And if you're done with BRF3, can you do XEF5, please? XEF5 plus. I want you to do, not quite, almost. This is an expanded octet. Okay? So the central atom would have more than 8 in this case. Right? So just double check your number again.
So you get the valence electrons,
Right.
and then how do you find the preferred again?
Now, the things that are not the central will always have 8 or 2, so hydrogen prefer 2. In this case, fluorine would always prefer 8.
So for bromine,
Try to do the calculation using bromine having 8, and see what happened with the number of bond that you get.
so, and then fluoride
Is
prefers
8.
so 8 times 3,
That's 32.
32, and
So,
there's a 4 difference.
so how many bonds you get?
2 bonds?
How many fluorines do you have?
3.
So there's not enough bond, right? So that means our guess is incorrect. You need one more bond, so you're going to add 2 more electrons in bromine.
So make it
10. Yes, if you get 10, you're going to get 3 bonds. And then you're done, right? You don't even have to finish the calculation since you know it's going to give you 3 bonds anyway.
Okay.
Yeah.
Is this right for the valence electrons?
Yeah.
Okay.
So the point is that even if you guess incorrectly, you would still be able to find out if you just figure out how many bonds that you needed. That looks right. All right. Yes. Thank you. What's up?
7 has 8, right?
Prefer number?
This is the preferred.
Oh, bromine is right here, so it has 7. Yes. Yeah. And again, if you calculate it incorrectly, you'll still be able to figure out by some. Yep. Thank you. Yes. All right, so I see quite a bit of people already done with this one. And if you want to finish and continue with the next one, do XEF5. This is just an example with plus charge. So you have some experience with the plus charges again, just a bit of a review. Don't forget, whenever you have a plus charge, you put everything in a bracket and plus 4. And a plus sign on the outside. And remember, a plus charge means that you have 1 plus 1 means 1 less electrons. So that's going to affect your calculation a bit. So let me finish the BRF3 here. 7 plus 7 times 3 equals to 28. The bromine in this case will prefer 10. 30, 24, 32. Hold on. 8 times 3, 24, 34. Okay, so we'll do this one for now. So you've already put this thing. So let's assume that you put in 8. If you put in 8, what is the sum of this whole thing? 8 plus is 24, plus 8 is 32. So what is the difference between 28 and 32? Wait, hold on. Yeah.
6 and 2.
Yeah, that's right.
6 and 2.
Sorry?
This would be 6 and this would be the 2.
I'm not sure what you mean. What's the difference between 32 and 28?
Hold on, I'm just gonna.
Yeah, that's fine. 4. So if you have 4, how many bonds that you have? You divide it by 2, so you get 2 bonds, right? But see, you don't have 2 bonds. You have 3 fluorines, so you need to have at least 3 bonds, right? So that means your guess is incorrect. This 8 is incorrect.
So that means I should try like 9.
No. So you just go from 8, 10, and 12. If you're missing a bond, you're missing a single bond because we have 3 fluorine. Go from 8 to 10. Oh, sorry, not. So that means your central atom have 10 electrons, in which case you will have 3 bonds. So even if you guess incorrectly, just, oh, I'm missing a single bond. Let's just move down the list. So it goes from 8, 10, and 12. Even if you guess incorrectly, you would still be able to figure it out.
Okay.
Yeah.
In this case, would you add like a
Not quite.
No?
Wait, how many do you put in?
It's supposed to be 5 bonds.
Yeah. If you put in double bond, and you have 6 bonds in total. Because double bond is 2. So, that's almost there. The central atom doesn't have 12 yet. Yes, that's right. Yes, yes, yes.
For this one, I'm a little confused because I know I have to get 4 bonds.
Yep.
But 12 is the maximum.
Hold
right?
on. Your valence electron is 7.
Oh, for fluorine?
Fluorine. Yeah, that's why the calculation mistake is happening. But otherwise, the idea is right. And all right, so let's do XEF4. XEF5 plus, and we'll finish off this particular example. So xenon, what is the valence electron in xenon? 8. Fluorine is, and I have 5 fluorine. Thank you. And I have a plus charge, means 1 less electron, so minus 1. So this is going to give me 42. And if I look at the prefer, now I'm going to again guess incorrectly, okay? So I'm going to guess incorrectly because that's usually what happens. And my educated guess is that my fluorine, there's 5 fluorine, so maybe there's 10 electrons in the central atom. So I'm going to put 10 for now because I'm guessing. I'm telling you now that it's incorrect. So if I were to guess this number, I get 50. And if I look at the difference between the two, I have 8 divided by 2, I have 4 bonds. Right? So that's an incorrect guess because I have 5 fluorine, but I only have 4 bonds to give. So I need to change this. Instead of 10, it needs to be 12, in which case this becomes 52. 10 divided by 2, so I have 5 bonds. So now it's correct. So xenon in the middle, and I'm going to cluster all the molecule on one corner, same as before. Oh, not iron. I keep writing that iron. And I'm going to give 8 electrons in each fluorine. Now my xenon prefer to have 12 electrons in its central atom. So far the xenon only have 8 because I have, am I missing a bond? I am, right? There's 5 fluorine, sorry. There's 5 fluorines to give. So I need to give my xenon a single lone pair to complete the structure. So that's more or less correct. But because this is have a plus charge, I'm going to put everything in a bracket and a plus charge on the top. Okay. So again, even if you guess incorrectly, usually what happens is that you either have too many bonds or too little bond. Just kind of move down the list. And then usually you'll get it right. Okay. We are about a little bit over halfway in. So I'm just going to do one more calculation. In this case, the calculation of formal charges. Now, sometimes when you have an expanded octet, it's not entirely clear. You can have several different Lewis diagrams that is possible, and you're not entirely sure which one is the correct one. Uh-oh, I ran out of battery. Hopefully I have enough charge to finish the class. So the best way to go in terms of whenever you have the times that you have to calculate formal charges is when you have anion with lots of oxygen. So for example, SO4 2 minus is the one where you probably have to calculate the formal charge to figure out which one is the best one. PO4 3 minus is another one where you probably should calculate the formal charge to figure out which one is the best Lewis diagram. Now the equation of the formal charge, I'm writing this down slightly differently than what you have in your lab manual, but they otherwise remains the same. The idea of formal charge is basically it's equal to the number of electrons that the atom have minus the number of electrons they actually have, right? And you can count this out that the number of electrons that it actually have is basically the number of valence electron minus the number of bonds minus the number of lone pair electrons. So let's actually do some calculations, and we'll do the one that's kind of easy. So in this case, we'll do CH4. Okay. So I'm going to calculate the formal charge of carbon. So I'm going to calculate the formal charge of carbon. So what is the number of valence electron of carbon? It's supposed to be 4. Carbon have 4 valence electron. And how many number of bonds that carbon have? There's 4 bonds, so 1, 2, 3, 4. So carbon have 4 bonds. And how many number of lone pair electrons that carbon have? So I don't see any lone pairs on carbon. There's no lone pairs. So the number of lone pairs is 0. So the formal charge is going to be 4 minus 0, and it's going to be 0. Okay. Carbon have 4 bonds, so minus 4. And there's no lone pair, so minus 0, because there's no lone pair electrons. And if I were to do the formal charge of hydrogen, and notice that all the hydrogen is basically the same on each one, so I don't have to distinguish which one. How many valence electrons does hydrogen have? 1. And how many bonds does hydrogen have? Just 1, just that 1 bond. And how many lone pairs does hydrogen have? Well, there's no lone pair, so 0. So the formal charge is 0. Right? So if I were to kind of put all the formal charge next to each of the atoms, you'll find that this is going to be 0, 0, 0, 0, and 0. Okay, because all the hydrogens are all equivalent. And in fact, the best Lewis diagram will have mostly 0 formal charge. Right. And if you want to know whether an atom have 0 formal charge, you just need to know what their preferred number of bonds to. So I see over here that hydrogen have 1 bond, and you know from the periodic table, hydrogen is group 1, so hydrogen prefer to have 1 bond, and it have 1 bond, so the formal charge is automatically going to be 0. Carbon prefer to have 4 bonds, and it already have 4 bonds, so the formal charge is also going to be 0, even without any calculation needed. And the best Lewis diagram is going to be the one that have the most 0 in its formal charge. So let me do another example. Let's do SF4, because I think SF4 is one of the examples that I haven't done. So the Lewis diagram